I have SAP 2000 version 24 open. You can use any version from 22.1 onwards. Let's open the plugin. We'll change the units across from metric to US, and we'll open the help file to guide us. So let's say we're building a vessel with a 66-inch outer diameter, a 1/2-inch thickness shell, a 12-inch branch. We'll cut through the header. Let's choose a repad width of 6 inches, and the thickness will be the same as the shell. For the branch angle, let's take a look at the next page in the help file. This is the angle here. So let's choose 60 degrees. The Hillside Offset is in the previous image. It's the distance between the center point and the center line of the nozzle. Let's choose 10 inches. You can also enter the leg length for the covering fillet weld. This doesn't produce an exact model of the weld, but rather it locally increases the thickness in the model. Let's choose 1/4 of an inch. Now the weld stress concentration factor, this captures stress raises at the toe of the weld. You can look up a standard such as ASME 8 Division 2 for an appropriate value. Quite often in the piping industry, in the past, a value of 1.35 has been used for similar assessments. This figure will be applied to all the 4 SIFs calculated. Let's just notice here also how the radial axis goes from the center point of the shell out through the intersection point with the center line of the nozzle. The longitudinal axis is then tangential to the shell there, with the circumferential axis at 90 degrees acting out of the page here. These will be used for all the stiffness calculations. Looking at the distance to the rigid ends, this will be the distance to a stiffness such as a flange or a vacuum ring or a head. Normally you'll have this information from the vessel drawing. So let's enter some values here. If you're dealing with a piping application, you may not know this information. So what you can do instead is leave these fields blank, and then the plugin will assign what it calls the default flexible length. This will tend to result in quite a long length for the header, which tends to offer a high SIF. But at the same time, the flexibility of that intersection will also be on the lower end. So if you do happen to know the length to a stiffener, which may potentially stiffen that intersection, it's better to use that if you have it. The branch standout similarly is the distance to a stiffener from the intersection point with the shell. The mesh size, that can be altered in a range of 1 to 5, using 1 for the finest mesh and most accurate results. But using a value of 3 will still give good results and it will run slightly faster, so let's use that for now. So the program starts to build a beam model first. We have 2 views of the same model. On the left hand side we'll shortly see the deflected view. We then delete that and continue building the shell model. While the shell model is being built, let's just go over why we build a beam model in the first place. What we want to do is avoid double counting the stiffness of the beam. So first we solve the model as a beam and we retain that deflection. We then solve it as a shell model and we subtract the beam deflections before calculating our flexibilities. In this shell model you can see by the green symbols that we've fixed only the base joints. This is for calculating the SIFs. That solves quickly. We get that information, we delete those results, and then we add fixity to the top as well. and we resolve this model in order to calculate the stiffnesses. This will solve pretty quickly, and we'll get a message coming up saying the analysis is done. If we want to look at the FEA model, we can do that, but first we would need to close the plugin. But first let's take a look at our results here. So you can see the stiffnesses and SIFs have come up at the bottom. We have the radial stiffness, which is the translational direction inwards to the shell, and then we have the rotational stiffnesses, and then of course the SIFs being the radial direction intensification factor, and the in plane, the out plane, and torsional. Now these are all for the branch, not for the header. You can also save an RTF file, which will save your inputs and outputs for the record. Now the RTF file will contain flexibility factors which aren't shown in the plugin graphical view here. I'll just bring up the file, which should open in Word. So firstly our input listing, followed by our stiffnesses and SIFs. And these are the B31 flexibility factors. These can be used in lieu of the stiffnesses in a program such as CSI Plant or other pipe stress programs which let you enter custom flexibility factors. Just note that they only capture rotational stiffnesses, not radial. So if you need to capture that one as well, you would need to model a separate anchor with flexibility. That's why I would generally tend to use a flexible anchor rather than using the flexibility factors. We also show the lengths used in the FE model, which is useful to know if you'd left those fields blank. Okay, so if we'd like to have a look at the model now, we firstly need to close the plugin and wait while it hands back control to the program. I like to use the orthogonal view and also to fill in the mesh. So on the left here we have the deformed view for the radial load case. Let's just rotate that a little more. So you see here it's the radial load case. On the right we have the undeformed view. You can zoom in, take a look at the mesh, see that it's nicely formed. You can change the view type to extruded. This will bring up the thickness of the plates, and you should see the reinforcing pad sticking out a little bit. So let's have a look at the stresses. So we pick shell, we're going to look at the radial load case, shell stresses. We'll pick the absolute maximum stress and SVM, the von Mises stress, and we'll turn off averaging. Okay. So you see in the load scale that the peak stress is up to nearly 4,000 psi. That will just be a very localized stress, of course. As you mouse over the individual points, you see the values of the stress at that location. Highest stresses will of course tend to be in the intersection points. So in the actual weld zone we do ignore those stresses for the SIF calculation. So I'll just show you how that's treated. We actually have a group that's named weld zone, so you can select that group. We have a group called weld zone. There's another one called stress check, which is the inverse of the weld zone. So selecting the weld zone, it's the elements within the thickness of the shell and any covering weld. We can also hide those elements if we want to. So we would do remove selection from view. So now we're showing only those elements which are used as part of the SIF calculation. We'll tend to see the highest stresses in the base of the nozzle, particularly if the nozzle is thinner than the shell, or at least the shell plus the repad thickness. And that, my friends, is an overview of the Nozzle FleX plugin for SAP 2000. Let me know any comments or questions, and thanks very much for your interest.